the stress will go in a direction that will reduce the system so that the equilibrium is re-established. Okay, so for you to re-establish the equilibrium, then the equilibrium must be such that when you disturb the system must get back to the equilibrium. Okay, so let's start with simple ones. Let's say pressure. These are gases, so pressure will. Let's see how to go. Now this is in the system. If we increase pressure, in which direction will this reaction go? So the reaction will go in the favor of the part of the reaction where there are fewer molecules. Because if there are fewer molecules, then the pressure will go down. So see that here we have how many molecules? 3. And here we have what? 1. So if you increase pressure, will the reaction go this way or that way? If it comes this way, it will be generating more molecules. So you have more pressure. So it will rather go that way. Okay? That is how pressure is going to happen. So you see, when pressure is increased in this system, the reaction will shift to the right. Okay? Now, let's look at volume. You know, volume and pressure are related, but pressure is what inversely proportional to volume. Okay, so let's see. If we increase if this one was in initial volume, let's say initial volume like this, and then we increase it to this. When you open up the space, pressure, what happens to pressure? Pressure will go down. Okay, so the same as saying when pressure goes down, how can you increase pressure? Then the reaction should what? Go in the left direction so that it will generate more molecules to fill up, so that pressure is brought back to the same point. Okay, so that pressure and volume will have like the opposite effects. Okay, so if you increase pressure, the reaction will go that way. If you increase volume, the reaction will go that. Because if you increase volume, it's the same as reducing pressure. Right. Okay, so when you come to temperature will come with a different thing. The point is, if you increase temperature, the temperature is going to change the rate of reaction. Okay, it's going to change the rate of reaction. So it will rather alter the equilibrium constant. So it will change the equilibrium constant. Assuming an enzyme was an enzyme, let's say assuming an enzyme. An enzyme is a catalyst. A catalyst is anything that will facilitate reaction. Okay, but itself will not take part, and itself will not be converted. Itself will not be changed in the reaction. Okay, an example is an enzyme. An enzyme will help a reaction to go on. So it's a catalyst. Now, if you increase temperature, I see that you may change the conformation, you will change the size, the shape of the enzyme. Because the enzyme is protein, when you heat it, it will change electron. When it changes, it may favor a certain path more than the other, so that at the end, the ratio between this and that will also change because of the way the reaction has changed. Okay, so temperature will affect the. Okay, now let's look at the last scenario where we have, let's say, moles. We are adding more moles. So let's say if we add more A gas to this system, what do you think will happen? If you add more A, the reaction will shift to this side, so that the A that you have added will be consumed. Okay, so if you add more A, the reaction will shift to this side, so that the reaction will be consumed. Okay, so if you add more C, the reaction must come here so that to consume the one that you have added. So this reaction is always by mass action. I mean, they are coming together to make sure that they deflate the stress that you add to the system. That's the mass action. So let me, instead of entropy, I'll add entropy to this side, and then we'll discuss acid base here, because that is also related to this kind of equation. I'm putting them together so that, because the analogy is similar, you'll be able to acid base. Then we look at pH. Okay, so when you say pH, what do you mean by that? Okay, so we have talked about how adding moles will change it, how changing pressure will change it, how volume will change it, but temperature will change the whole constant. The rest will not change the constant, but they will change the direction of the reaction. Okay, but temperature will change the ratio of the reactant, so it will change, it will bring on a new equilibrium which will be different from the first one, so the K factor will change. Right, so that is that for the acid, the gaseous part. So we have dealt with general equilibrium, dealt with solubility, dealt with gases, and then changing Le Chatelier's principle, and then we dealt with rate of reaction. Now let's look at acid base. Okay, an acid, according to Bronsted law, definition of acid, acid will be anything that will generate H plus, okay, in solution. So let's say I have this H let me make it the general formula for acid. So an acid will be H plus, and then the base will be OH minus. Okay. Right, so let's say I have this HX. This is an acid. It's broken down to H plus what? Minus 1. So this is the equilibrium reaction. Okay, this is the acid. Let's say it's a weak acid. If it's a very strong acid, it will go almost, you have almost little coming back. So a lot to go. It's almost going to be almost irreversible. Okay? But let's say for a weak acid means it doesn't dissociate to give you more hydrogens. That's a weak acid. And the weak acid, they are usually, the weak acids and the weak bases, they are good buffers. Okay, when you say buffer, it means it's something that will, when you put on stress, that the stress can be, it will help to absorb the stress. Okay, so the weak bases and weak acid, they are good buffers, so that when you add on an acid or base, they will take care of the excess acid that you have added, so that the acid doesn't show up in the system or in the solution match. And that is needed in our body. If the pH, the concentration of acid is kept constant, the enzymes will be able to work at that point. So that when an acid is added to the body will find a way to sort of take off that the extra acid that was added so that it comes back to the same acid concentration. The acid concentration is related to your pH. Okay, we'll look at that. We'll come to that one soon. Okay, so let's look at the general formula for this and apply the same principle for K constant to derive equations for the acid. So here, if you are writing the equilibrium constant for this reaction, then K is equal to what? Product over what? Let's say this is aqueous, this is aqueous, this is aqueous. So because they are all aqueous, we are applying the equation. And this is our HX. Okay? Right. So if we have this is the equilibrium constant. Now what happens is when you are dealing with bases and acids, they are usually in 10 to the powers. So let's say exponents. Okay, if you are dealing with figures which are in exponents, you are better off converting them to logarithms, to logs. Okay, so it will be better for us to convert this equation to log. That is why we would want to apply the log system. Now P can be a symbol that we use to represent negative logs. Okay, negative logs. So we'll apply this one here to derive the Hesselberg equation. Okay, Hesselberg equation. Okay, so let's see how we can put that one in. But remember this what you said. So remember negative log presenting T. Alright, so let's see how that can be put into the equation. So Hesselberg equation is what we are going towards now. Let's see. So here, this is our K. Okay, because it is a constant for acid, you can say Ka. That is acid dissociation constant. Okay, good. Now, if we take log of Ka, we must take log of this side too. So why am I writing E? Over HX. Okay, so there's it. Right, so let's see what happens. I don't want us to get confused from this one, so I will not add the negative. When I'm getting to the end, I'll add the negative so that we have to. If I put it here, it will create a lot of confusion here. Right, so at this point, our log Ka will be equal to, because log, when it is multiplication, it's flat, so this is actually going to be what? Log H. Okay, plus, let's make it log X over what? HX. Let's put it this way. Okay, right. So this log, the reason why I've made it this way is I want to get an expression for log H hydrogen concentration, because pH is the same as negative log of the hydrogen concentration. Okay, that is why I'm trying to get an expression like this here. So it's not just the chance that I'm putting it here. I want to get an expression like this. And then I have the rest can be any expression in terms of fraction. Right, so at this point, this is what I have. I can multiply through by what? Negative 1. Okay, so this will be negative, this will be negative, and this is going to be what? Negative here. Okay? Right, so from here, what are we going to get? This is the same as saying, we said negative log is the P. Okay? So you can put P in place of what? Negative log. So that we're going to have P Ka is equal to what? pH minus what? Log X. Let me make it simple so that we don't have something like that. The concentration should be there. Alright, so this is the equation. So this is the Henderson-Hasselbalch equation. Now, if we look at, we can rearrange them properly. We can bring this one as minus so that we have a positive distance. So that I can have PA is equal to what? PKA. This is crossing, so it becomes as what? Log of what? X over HX. So this is the equation. Henderson-Hasselbalch equation. Okay. So when the pH is given, if you are asked to find the pH, if you know the pKa and you know the ratio of S to X, that is the part of an acid which is dissociated, and then the undissociated acid, you can find the pH. Okay, that's it. You can also look at the equation very well. When would pH be equal to pKa? When this ratio is equal to what? 0. So if you equate this one to 0, when you equate log X over HX equal to 0, what happens? This is log to the power 10. Okay, so you can take antilog so that it will X 10 to the power 0. Okay, if you take antilog, it will become this 10. So it becomes 10 to the power 0, which is the same as 1. Any number to the power 0 is 1. So this will tell you that X is equal to. So when X is equal to this, when X is equal to HX, this becomes 0, and then your pH is equal to your pKa. Okay, so your pKa is your pH when there's full dissociation. Absolutely, this whole thing has been converted to X. That is a very, if you have almost everything going into that direction. Okay, so that's the picture I want to create. So we have also dealt with the acid base part. So note the same thing can be done for OH. So we are trying to have how many equations here? 1, 2, 3, 4, 5. Then the last bit will finish everything. Okay, but you see that the same concept, because it's the same concept, you're able to grasp it easily. You can relate that, you can relate this one, you can relate that, you can relate that, you can relate that. Okay, this one is for differentiation. Our maths that we dealt with, so you should be able to. Of course, the last thing I didn't say about this one is when you are doing the, if it is 1 over a to the power 2, you see length cannot natural log the natural log system will not work, because it will not be the difference. The top one will not be the differentiation of x. So it means you have to use another method, and that was why we use raise it to the negative and then integrated it like normal integration. So that's that. Now when you come here, we have discussed how the acid base reaction will go. At the end, this is the equation we are having. Henderson-Hasselbalch equation. Okay, now the point is, if it is OH, how are you going to do it? I think the same thing will go. What we'll do is, let's look at it. It means this equation is going to go off. So I'm just giving you the principle so that on your own you can try to derive the equation. If you are able to derive the equations, when the questions come, you will know how to deal with them. So this is by saying that I have what? Let me make it KOH. Okay? Or let me make this one X. Okay? So this is a base. Base must have OH. Okay? Becomes X plus what? OH minus. Okay? And so the same substitution I put this. So it means that here, instead of O, it will become what? It will become OH. And this is your S. So wherever this one will be, H will be, you put your OH there. Okay, so this one will become what? Negative log bracket OH, which will become what? POH, okay? And this becomes POH, okay? So the reaction, the formula will go in that order. Okay, so it's just getting the first concept and then extend it to the other ones. So sometimes, fine, it's good to get the formula in mind, but when you are struggling to get the formula, you can go through the steps, the first principle steps to derive the formula. So that is for acid base. So that will bring us to the end on that side. Now let's move to Gibbs free energy, where we look at all the factors that will determine how a reaction will go on spontaneously or will not be able to go on spontaneously. Let's look at that. So I'm leaving all this on the board. You can pause the video and then look at it. You see the similarities, okay? And it will make your learning very easy. Okay. Alright, so that's one of the concepts of our teaching. Right. So to make things easy, we try to relate things. So it's that in actual sense, there are a lot of topics that we have done. When you go back, you realize it, but you won't see it now. As you go, you realize, oh, it's a whole topic that we have dealt with in this small context, okay? So this is designed to make people appreciate similarity, and then it makes learning easier. Okay, so let's go to Gibbs free energy. Now, from our discussion in physics, of course, I've told you, for us, mathematics is the basis. You should have a very strong base in mathematics. Then you come to your physics, okay, so that you know how to relate reasoning to how things happen naturally, and then artificially, how we have brought things together to function, okay. Then you come to chemistry, okay. So at the time you get to chemistry, we would assume that you have gone through our steps as mathematics, elective mathematics, and core mathematics, the physics aspects, and then we come to chemistry. So let's see how, let's recall what we did under physics. You remember we said the change in enthalpy is equal to the change in internal energy plus what? Work done, which is the constant pressure times volume. Because it's change in enthalpy, it could have also been change in heat is equal to change in internal energy plus the pressure times the change in volume. Once it's constant pressure, this heat becomes enthalpy. I've said that heat change, exchange in a reaction where the pressure is constant is referred to as enthalpy. Okay, if the volume is constant, it's referred to as internal energy. The heat exchange, the heat that is involved, not exchange, the heat that is involved becomes internal energy. Right. That means the part of the internal energy, the total energy within the system, is converted to work or something else in the system. Right. But there's no exchange between the system and then the surrounding. Then of course we are looking at more like an equation of a scenario of adiabatic, what do you call it, a scenario. Okay, good. So here, look at it very well. We want to relate this to a new concept. Okay, now before we go on, there's something we call entropy. Now in simple terms, because we are not going so much into details, but to get a concept and then be able to relate things. Entropy simply means disorder, okay? So every system is trying to get into a disorder kind of thing, okay? Everything is always trying to get in the system, the whole system, universe system, everything is always trying to get into a disorder, okay? So if you want to put things in order, you need to add energy. But if things have to go in a disorder, then it is more like a spontaneous kind of thing. Okay, so the greater your disorder is the greater entropy. That is the greater the different arrangements. Okay, would mean that you have greater entropy. Right. So we'll factor that into the equation. Now we said that this represents the part of work. Now it gives free energy is given by the change in G. We call that G. Okay. Now this G is related to the work done. That is the energy that is available for work to be done. So in your body, it's the gives free energy that allows body functions to go on. So this is related to the work that is supposed to be done in your body. Right, so we can rewrite this equation as then change in enthalpy, and that is if we are dealing with constant pressure, as happens out there. The body, the pressure around us is fairly constant, okay? Then we can assume we are dealing with enthalpy. Is equal to change in internal energy plus what? Our gives free energy. We have replaced this one by this free energy. Now I'm trying to create a very simple path for us to understand this, the equation, so that we can apply them. Good. Now if we move on. Now this internal energy, we said, depends on the temperature. Depends on the temperature. So that temperature is also dependent on the kinetic energy of the molecules involved in the system. Okay? So that is, it will depend on temperature. So it depends on temperature. Let me define it here. Okay? Now, of course, in our body, the temperature is constant, so I will not make it change in T. I'll just make it T. Now, this same thing here, the entropy, the disorder, the internal energy is also measuring the disorder, either vibration, rotation, and arrangement, and all that. Okay, so we can also say that let S be entropy be S, then we can say this is change in S. So at the end, this is the equation we are having. I always prefer to go this way so that my students will understand how to get the equation, not to memorize them. Okay, and to relate things. If you are able to relate things, it makes your judgment of questions very easy. So at this point, this is where we got into. And this is the equation I want us to look at. Right, so if we rearrange this equation, then you see that if we rearrange this equation, we're going to get something like this. Rearrange this equation, we're going to get gives free energy is equal to, this is crossing the equal sign, change in enthalpy minus what? T change in entropy. This is the equation we're looking for. So that is the equation. Okay, now let's look at this equation and then try to predict when a particular reaction is likely to go on spontaneously. That means it's likely to go on without any push. Okay, so when a reaction will go on naturally, then we say it is spontaneous. If you need to add something, then it is not spontaneous. Okay, so in a process that will go on naturally, it doesn't matter how fast it will go on, but once it can go on naturally, then we say it is a spontaneous kind of thing. For instance, if you have a ball on a hill, it can roll down, it will roll down naturally without any help. Okay, so that will be a kind of spontaneous process. Okay, right. So if you have, let's say, a hot liquid here and a cold one, you put them together. That hot this thing will be transferred into the cold, and at the end you come to a constant temperature. So naturally it will not be cold to hot, to rather go that way. So that is a spontaneous kind of process, right? So this spontaneous or spontaneity, we can look at it, we can use it to predict how how chemical reactions are going to be, to tell how whether a chemical reaction given to you is going to be spontaneous or not. Now, when there's energy done by the system, or energy is released, okay, when you release energy, you become more stable. So usually systems will prefer to go through a process where they will release energy and become stable. Okay, if you become so stable, you won't go back. Then the system would, you'd have come to an end. For that particular moment. So for when the gives free energy is negative, it means this tells you when this part is negative, it means part of what this part of the internal energy has been converted to work. Okay, and that process will be spontaneous because heat has been lost, so the system becomes stable now because it has lost something. Okay, so negative G or negative change in G or negative gives free energy tells you that the reaction is what? Spontaneous, response. If it is positive, it tells you it is not spontaneous. So based on this, we can evaluate the effect of enthalpy and entropy on the spontaneity of the spontaneity of the process or the reaction we are talking about. Okay, so at this point, let's look at it. Right, so let's see how this we can make this. So for a spontaneous reaction, it means G must be negative. How can G be negative? G will be negative if this part is negative. So if this part is very high, so if temperature is very high, then it's going to be negative. If the change in entropy is also very high, that is if it is negative. Okay, remember this, if it's also very high, then this whole thing is going to be negative, and then it's most likely it is going to make this effect. Assuming we are holding this constant, then it's going to make this one negative. Okay, and then we have a negative. So now the entropy is high, temperature is high, then it's most likely going to be negative. So that means that reaction. So if you are more disordered, if there's more disorder, and then there's more, the temperature is also high, okay, it's most likely that kind of reaction will go on. Okay, good. Now let's see if temperature is low, okay, and then there's a what do you call it? The entropy is high. Then it means it will depend on the ratio to compare with the change in enthalpy. So that will depend on certain factors. Now let's look at another. If the enthalpy here is negative, let's say the enthalpy is exothermic reaction. It's exothermic reaction. That means it's negative. Once this is negative, if this part is also negative, then it's also going to be negative. So if this is negative, let's see how this can be negative. If this is negative, and let's say entropy here, enthalpy, temperature times this one is also negative. So now if it is exothermic and then the entropy is in the negative sense, temperature is always being given as positive. So if you multiply it, you're going to get negative. This is going to be positive, and that will make your reaction. It's going to reduce the positive, the negative sign here. It may make it positive. Now, if this is positive, entropy is positive, and temperature is also high, okay, then what do you think will happen? It means this part is going to be a greater negative. This is already negative, and you're going to get a more spontaneous reaction. So you can evaluate this based on to see when you get negative. For you to get positive, let's say this endothermic is positive, okay, and then this one entropy is down, okay. If entropy is down, temperature is also low, then you know this part is lower and it's going to be positive. So that reaction is not going to be spontaneous. If a reaction is not spontaneous, it doesn't mean it can't occur. It means it will require energy from maybe the surrounding to be able to go on. Okay, spontaneity. If you are not spontaneous, it doesn't mean that reaction cannot occur. It's different from what you call irreversible or reversible reaction. Okay, so reversible, it means it can go back and forth. Irreversible means it is only one direction. It can only go forward. It can't come back. Right. So that is that kind of the picture. All right. So that explains this part of the equation I wanted us to analyze. So this is it. Good. So at this point, I think we've gone through the process. So what we can take as summary is the general equation starts with A plus B. Okay, and then as they are reacting, they get to a point we call the equilibrium point. At that equilibrium point, when the products are being formed, the products are also forming the reactants. So when the rate of forming the product is equal to the rate at which the product is forming the reactant, then we say equilibrium has been reached. The equilibrium that has been reached depends on the individual components which are in gaseous or aqueous state. If they are in solid or liquid, they don't usually contribute. And therefore, when you are writing a ratio, you realize that when you write a ratio of the product raised to their stoichiometric powers, stoichiometric figures, that ratio is always constant. To give you a constant figure, so we call that equilibrium constant. That is the equilibrium constant. Okay, so it takes care of only aqueous and then gaseous states. Like we said, those ones contribute to the back and forth reaction that is going on at the equilibrium. Okay, good. So solubility is the same thing. Solubility is a reversible reaction. Okay, so they dissolve. You can dissolve salt in water. Okay, that is also reversible. Maybe if you start evaporating the water, the salt will condense. Or if it was a very high temperature, if you cool it, the salt will condense. Okay, So it is both forward and backwards. That kind of equilibrium. So the same equilibrium equation can be set for it. But here, salt is solid, so it will not appear in the equation, only the aqueous one. If you come to gases too, we have said gases also contribute to maintaining constant equilibrium. That is what we have shown here. Various stresses can be put on the system. Number of moles will change. If increase number of moles, the reaction shifts to where it will reduce number of moles for that substance. If you increase pressure, the reaction will shift to where pressure is low. If you increase volume, the reaction will move to where what? It will seek to get to a point where the pressure in the system will be maintained again, because pressure and volume are related. Okay, temperature will change the rate of reaction. So it is going to change the dynamics at equilibrium. There's a new equilibrium going to be set. So K will be changed. Okay, right. Then we came to rate of reaction. So the rate of reaction is dependent on the components in the reaction. Okay, if you relate it to the reactant, then it will be what? You are consuming the reactant, so it will be a negative. It will become what? The rate will become negative. Or let's say the rate will be equal to negative dx over dt. Okay. If it is the product, then it will become positive. Positive dy over dt. Okay. So that is how it's going to be. Okay. Then you relate it to, you'll be told on this, dependent on this, the factor is to the power 0. That means 0 order. Or the factor is to the power 1. That is the first order. Or the factor is to the power 2. So second and so on. Okay. So that is going to tell you how the rate is related to. Once you get the order, you can derive the equation, the relationship, by going through the process of what? Simplifying and then integrating, then you get the answer. When it comes to acid-base reaction, okay, for a weak base, the reaction, because it's not able to dissociate completely, it dissociates a little and then the product will form it back. So as it is dissociating, it is also recombining to form the reactant. Okay, so in that case, it is a reversible reaction. So at the point, the rate of reaction going forward, the rate of reaction coming back become equal, and then we say equilibrium is what? Equilibrium is what? Established. Once equilibrium is established, the established equilibrium will mean that K. So once you have established equilibrium, will mean that the reaction here, or let's say the product of this over the product of this one should be the same as that. Okay. Alright, so let's see how we can get to the next one. Alright, so that is it. So once you get to equilibrium,